Welcome to the GenAI architecture series, where we don't just say agents did it, but we look at what the system actually looks like when you wire it up. Today we are talking about Anthropic's engineering write-up on building a C compiler using an agent team setup with Claude Opus 4.6. So yes, they built a C compiler that can compile C code, generate machine code, and even compile the Linux kernel. I'm going to focus less on how compilers work and more on the GenAI architecture choices that made this possible. Because the interesting part isn't LLMs can write code. As everyone knows, plenty of models can write plausible code. The interesting part is how do you set up a system so it can keep making progress safely without a human hovering over it every minute. The headline numbers are 16 parallel agents, around 2 weeks of work, about 2000 sessions, and $20,000 of compute. If you are thinking that's a lot, yes, it is. But also, if you have ever paid for a few months of human team plus coordination overhead, you will quickly realize that it's expensive but not insane for a demo of this scale. One agent accidentally did pick inline bash and self-terminated the entire loop. That's probably the most human thing an AI has ever done. Okay, so what did they build? The artifact they produced is a repo called CCC, Claude C compiler. Around 100k lines of code written in Rust and intended to be fairly self-contained. It has a front end, an intermediate representation, optimization passes, multi-architecture code gen, and even its own assembler and linker. And the funniest architecture detail is probably the README. A human literally says, I wrote this paragraph and please don't use this code. That is probably a very strong disclaimer. So yes, it's impressive, but the bigger question for us is, especially from the GenAI architecture perspective, is what's the system design that made the model effective? So let's talk about the real star, the agent teams architecture. So here is the core architecture, and it's gloriously simple. You might expect a fancy orchestration system, a planner agent, tool routers, structured workflows, a database, event streams, dashboards, but their core loop is basically Git plus containers plus log files. Each agent runs in its own Docker container. Each container clones the repo into a workspace directory. The agent picks a task, edits the code, runs the tests, and pushes the changes back upstream. It then pulls others' changes, merges, resolves conflict, and pushes again. And that's how the session ends. Then the next session starts in a fresh container with a clean state. Repeat this enough times and you get a compiler. Task coordination is also hilariously low tech. They maintain a folder that represents the current task queue. If an agent wants a task, it creates a log file, like current task fix parser bug.txt. That file is basically the agent yelling, I'm on it, nobody touch it. When the task is done, it deletes the log file. So the entire multi-agent scheduler is a folder of text files. Not a database, no queue service, just a directory and vibes. Because nothing says distributed systems like a folder of vibes and merge conflicts. This is exactly the kind of thing that makes engineers uncomfortable and probably happy at the same time. Because it's extremely simple, and it's also exactly how a lot of production systems secretly work. Merge conflicts are frequent and the agents often resolve them, which is either a sign of progress or a warning label for the entire future of software. Okay, now let's talk about the human inputs that made it work, the secret sauce. The post is very clear. The hard part wasn't Claude writes code, right? The hard part was building the environment around Claude so it can keep going without a human babysitter. In GenAI architecture terms, the model is an engine, but the surrounding scaffolding is the vehicle. The biggest human inputs are tests and evaluation. They used strong compiler test suites. They ran lots of real open source projects as integration tests. They added continuous integration rules that block regressions. Because without CI, a multi-agent system will absolutely break last week's fixes while improving something else. Another key human input is formatting feedback for the model. They explicitly say write tests for Claude, not for humans, meaning don't dump massive logs into the chat context. Instead, print short summaries and store detailed logs to files. This prevents the model from drowning in noise and keeps the prompt stable. So the big breakthrough is not AI can code. It's someone finally wrote a test harness that doesn't spam the model with 7,000 lines of nothing. Humanity advances slowly. They also designed around time blindness. Models don't really feel time, so they can burn an hour on something that looks like progress but it actually isn't. So they built a fast mode that runs a deterministic subset of tests. The agent quickly gets a signal. Did we get better or worse? This is classic autonomy guardrail, shorter feedback loops. Another guardrail is ephemeral containers. Every new session starts clean, that reduces flakiness and makes runs reproducible. But it also means the repo must carry the memory, good docs, status files, and the task conventions. In other words, your system state is not the agent's memory, it's the artifact plus process. If you're building GenAI products, this is the pattern. Reduce ambiguity, compress feedback, and make correctness measurable. Okay, so why parallelism worked? And of course, there are parts where it didn't. So, architecture lesson number one, parallelism only helps if work is genuinely parallel. When there are many independent failing tests, you can give agents separate tasks and they don't collide much. That's where this shines. But when the task becomes one giant bottleneck, more agents doesn't automatically make it faster. And they hit that wall with the Linux kernel. Kernel compilation is a huge integrated target. Agents started stepping on each other's toes. They would fix the same bug from different angles, or rewrite the same files differently, or resolve merge conflicts differently. At that point, 16 agents is not 16x faster. Sometimes it's just 16x chaos. Their workaround is a clever architecture trick. Use an oracle. Specifically, use GCC as a reference compiler to isolate where CCC is failing. Compile most files with GCC, only some with CCC, and find the smallest set of files that triggers the failure. Now you can distribute those smaller, more isolated tasks across agents again. This is very GenAI productist pattern. You don't brute force. You reshape the problem so the system can make steady progress. So very quick note on the compiler itself without going deep into the compiler theory. Internally, the structure is fairly standard and modular. Front end to an IR, then SSA promotion, then optimization passes, then backend code gen for multiple architectures. This matters because it's not a random blob of code. It's a pipeline with boundaries, and boundaries are friendly to agent teams. You can assign work by module, parser, IR, passes, code gen, assembler, linker. You can validate each through focus tests. That's the alignment between software architecture and GenAI architecture. Modularity enables safer parallel agent work. So now the important caveats. First, this is a domain with lots of existing examples. Compilers are not mysterious. There are decades of patterns, open source implementations, and textbook architectures. Even if they blocked internet access during the development, a model trained on public code likely already has a decent prior about what a compiler looks like. So yes, it's impressive, but it's not like the model invented SSA yesterday. Second, the real world products are messier than a benchmark target. In product work, requirements are ambiguous, interfaces shift, security and privacy constraints exist, performance matters, observability matters, and half the time the issue is not write code, it's understand what the user even wants. Third, lastly, even their own write-up shows not fully solved edges. There is a part of the boot flow that still relies on GCC, and they mention certain components being buggy at demo time. Also, the generated code is generally not as efficient as mature compilers like GCC, which is not surprising. GCC has had an unfair head start of several decades. So yeah, it's a self-contained toolchain except for some parts where it's not, which honestly is also how most human software works. So that's completely fine. So yeah, here finally my takeaway. The compiler is cool, but the bigger story is the multi-agent harness design. Parallel agents, tight tests, short feedback loops, and strong regression control. It's an architecture that treats the model like an engine, not like a magician. You don't ask it to be correct. You build an environment where correctness is measured continuously and failures become actionable tasks. Because the best GenAI architecture is not the one with the fanciest agent diagram. It's the one that still makes progress even when an agent decides to take down Bash. That's it for this episode of GenAI architecture. Next time we will pick another real world system and extract patterns that we can use.